What about some other properties that are less computational? So there's a bunch of properties listed here that are more about relationships. So here, if we have a function that's greater than 0, then what we're told is that the integral is going to be greater than or equal to 0. Well, again, all that's capturing is if our function is above the axis and we take the region underneath of it, it's going to be a positive area region. Another way to think about this is from sines. If we have positive f of x values, and we're always using positive delta x values, which is what we get when we increment from a low value to a high value for a to b, then our sum in our integral is going to be positive values times positive values, and guess what? We're going to get positive values when we're done. These other relationships follow a similar kind of model. If I have a function that's always higher than another function, then if I look at the area underneath this function and the area underneath this one, they're going to have the same relationship. So again, we can do a quick sketch of that. If my g is the smaller one and f is the larger function, then maybe they touch it one bit there. And then we take integrals over a specific interval from a to b. It's clear that the area under the g, represented by this integral, is going to be smaller than the integral represented underneath the graph of f of x. And so that gives us some building blocks to work with. We'll look at these next two in a little more detail because they're maybe a little more complicated. The f of x, g of x graph actually is restated here. So that captures the relationship between the functions themselves and then the integral values underneath them. And then for this little m and big M model, all we're doing with that is trying to express something that could be potentially complicated or potentially difficult to calculate. Let's just say complicated for now. And recognize that we can put a bound on that integral, a very simple bound, but maybe not very accurate. So this is a very typical trade-off in calculus and numerical methods, is to have something that you'd like to compute but can't, and then you can replace it with something that you can compute that's wrong to some extent or off or has some kind of error built into it. But here it's a relatively straightforward argument that if we're concerned with the integral underneath this function here over an interval, if we pick any value, so this m here is going to be a height, just like f of x is a height. And if we pick any value that's lower than f of x on this whole interval, so say this guy right here, we're going to be able to get an area for that. And what's the area of that? Well, it's a rectangle, height times width. That for sure is going to be less than or equal to the area under the complicated curve. And we can do the same thing again with an upper bound that we call here capital M. Last but not least here, let's take a look at the effect of the absolute values in property 10. So imagine we have our graph from earlier with our 5 regions, and remembering that each of these contribute positive or negative totals towards the integral. The area interpretation of an integral only really makes sense if everything's positive. When you have negative regions that are underneath the axis, the area there is still a reasonable thing, but we have to treat it as a negative contribution to the integral. All right, so let's take a quick look at the statement here. And that's not too bad to see here. If we think of the curve absolute value of f of x, then how is that built? Well, when the function f of x is positive, we get no change in the function. However, when the function goes negative, then we are going to take the absolute value of that and we're going to make, say there's -1 here, we're going to make it +1. That has the net effect of reflecting the graph over the x-axis. Only for the negative regions though. On this next interval, the graph is already positive. So I'll line these things up here. This graph is already positive, and so we'd get the same graph back until we reach the region represented by D. That would again go positive if we're looking at the absolute value of f of x. And then last but not least, we'd have E afterwards. And then if we take a look at those two options and imagine adding up all of this area, And we talk about the integral of the absolute value of f of x dx, where this is our heights now. These are all positive and not going to have any cancellation. Contrast that with the integral of the original function here, where let's put different colors for the positive and negative. We're going to get a positive contribution for the a, c, and e integrals here, and the b and d values are going to actually subtract from that. Think of it as forward motion, then backwards motion, forwards motion, backwards motion. We're going to end up with a little bit of forward motion, but it's not going to be the straight sum of those 5 ingredients. And so actually what we get here is a minus b plus c minus d plus e. That's equal to the integral of f of x dx. That's the straight integral. Now, if we do what property 10 indicates, take the absolute value of that, well, just looking at the areas here, it appears that the areas of a, c, and e are already bigger than b and d together. So if we take the absolute value of that, this is already positive, so it's not going to change. But we're going to get still cancellation because of these negative terms, whereas this one here is simply a plus b plus c plus d plus e, and that's going to be larger than or equal to the sum that we get up there. So if we do the absolute value last, there's a possibility of cancellations. If we do the absolute value first, everything that we're adding up, or everything that's in our integral, over here, everything that's in our integral is positive, and so we get a larger accumulation when we're done. Now these can feel pretty abstract. Again, typically in a given scenario, it's much more obvious what kind of properties would be helpful to deduce some relationship, but these are ground truths that we can fall back on, or formula versions of those ground truths that we can fall back on if it's helpful for us to have a quick reference list.